Welcome to this course of Product Design and Value Engineering. In today's session, we'll discuss design for assembly. In previous session, we has discussed design for manufacturing, and if you have not seen that video, then please go and check that video first and then come for this session of design for assembly. In the previous video, we have discussed these elements of manufacturing cost, and we know that manufacturing cost can be affected by actual manufacturing of component, assembly and overhead, and we know that overhead is not something that can be affected by us largely. So we mainly focus on reducing cost on components and reducing cost of assembly. How to reduce cost on components, that we have already seen in design for manufacturing. Now in today's lecture we will discuss how we can achieve to reduce cost of assembly by changing our design, or how can we minimize our assembly cost while designing the product itself, and why we want to uh, reduce our assembly cost, and why we want to consider assembly while designing the product. Because as we know that once the design is final, we cannot affect the cost very much. As we have seen in previous video that design will uh, finalize 70 to 80% of the spending. Design will decide 70 to 80% of your spending, how and when it will be done. Once the design is finalized, there is only 20 to 30% cost saving that you can do. So while designing, we should consider assembly, because assembly compromises, or assembly consists a large sum of your cost, because assembly requires labors, assembly requires time, assembly requires equipments, and all this cost can be reduced if you are doing your design considering the assembly of your product or assembly of the system. And what should be considered while designing for assembly? So these are some guidelines that need to be focused on while designing for assembly. One is reduce these threaded fasteners if possible, because one study shows that threaded fasteners are 75% of uh, reason in assembly line defect. So on assembly line defects, 75% of the defects are due to threaded fasteners. So we are try to sorry about that. We will try to avoid as many threaded fasteners as possible. Instead, we will use different types of fasteners, because threaded fasteners are reason for defects, as well as threaded fasteners are also time consuming to fasten. So we will avoid threaded fasteners. Another is this very interesting concept of pokayoke. This pokayoke is Japanese term which means mistake proofing. While as designing for assembly, we tend to do mistake proofing. We design in a way that is not possible at all. And how can we do mistake proofing? So here are some example of this mistake proofing. This SIM card, we all know that SIM card has this slot, and what this slot does that it makes sure that SIM card is not inserted in wrong direction. So even if you want to, you cannot insert SIM card in a wrong direction. That means SIM card insertion is a mistake proof process. You cannot make mistake in inserting the SIM card. Similarly, in this example, we can see that a 3-pin plug cannot be inserted in a wrong way in a socket. So this is another example of mistake proofing. You cannot make mistake in inserting this 3-pin plug. while designing we while designing we keep in mind that our design should have some aspect of mistake proofing, so that the operator in hurry by mistake cannot make any uh, in hurry cannot make any mistake, because it will not be possible. And there are many ways we can achieve this mistake proofing. How? That we will see in a bit. So one is self fastening features. We have seen that we try to avoid fasteners, threaded fasteners as much as possible. So instead of threaded fasteners, what can we use? Instead of these threaded fasteners, we can use this type of clips which are fastened by itself. By just pressing it we can fasten the cover. So here in this base you want to mount this cover plate. For that you need to fasten these 4 screws. So for one cover plate you need to fasten 4 screws, and it will take time. In another design what we have done is that we have made this clip, and what we need to do, we just simply need to put it on top and give pressure. It will reduce so much of time, and this type of features should be added in assembly as many as possible. Then instead of selecting for fasteners, we'll first try to use snap fit, because it is least expensive. As we have seen in previous example, that was an example of snap fit. It is least expensive and we should try to implement it first. If this is not possible, then second option is plastic banding. Plastic banding is an example of another fastening techniques, and it is used in many places. So this is our second option. If even this is not possible, we do not have gap here, then we should consider riveting. And if even riveting is not possible, then only we should go for screw and we should go for fasteners, because from bottom to top our cost is increasing, our assembly time is increasing. So we try to achieve this first. Snap fist is our first option, then plastic bending, then consider riveting, and if it is not possible, then only go for screwing. And another principle is symmetry. Now what happens is, if your part is asymmetric, then worker need to reorient it, and it will take more time because orientation is needed. uh, if say some worker is working on this project, and here he need to fasten for screw, because the hole should be aligned. Now what happens is, if by mistake he uh, puts plate in, say he rotates the plate and put it with 90-degree rotation, then these holes will not align. So instead make your part symmetrical, so he can put in any direction you want, and there will be always orientation of this wall. This is an example of poka-yoke. This is the example of mistake proofing, because every alignment is correct, there is no wrong in here, and it makes symmetry much easier. The another principle is top down assembly. We want to start our assembly from bottom part, and then we need to keep on building it, keep on building it, keep on building it, because this makes assembly easy. So this is another principle. Then we need to consider the size of components and its shape so that we can handle it easily, so that worker can easily pick up the part and they can make easy assembly. If its size is too small, it will be very difficult to pick up, because there is a limited amount of shapes that we can pick up. If it is sharp by edges, the worker might get injured, and it will reduce the speed and it increase the assembly time. If it is slippery, then also it will increase the receiver. And if it is flexible, then what will happen is worker need to work with both the hand, because he need to orient the part in a different way. So it will also increase the time of assembly. We try to avoid all these problems. Then we try to address the insertion issue by providing self alignment and self location. How can we do that? Instead of doing this where parts can hang up at the corner, we give a chamfer here, so that spring will align into its place by itself. So this is what we can do, and we make design of parts such that we can reach in every area where the part need to be inserted. If your dimension of part is less, then we need to uh, we have to align it with our hand, and we need to simply release it. And if it does not fall in the hole, then we again have to repeat the process until it falls in the hole. Instead, we just make it longer, and it will be easy to assemble. So we are providing self-aligning and self-locating parts, so that assembly will be very quick. And this is also an example of self-location. We are we do not we need to worry about alignment of wall while we have designed for self-location. Otherwise, we need to align it with wall, and it will require time. Here is also an example of self location. Here, if we giving this type of design, then to make spring in its place, we have to give we have to be more careful, and it will require more time, while this type of projection will reduce this time, and it will self align the spring. These are also examples of the same insertion issues. Then there should be adequate access and visibility. Here, if we want to rivet our parts, then there is no place for hammering, because this portion of our part comes in the way. So we should provide some access. And same with the case with here. If we are doing some fastening below the seat, then it will be very difficult. So proper space and access should be given. And another thing to consider is to eliminate secondary operations. What we are doing is, we are simply reducing number of parts. We are simply reducing reorientation, screwing, drilling, all that, because we want to reduce as many parts and as many operations as possible. So instead of screwing 8 bolts, what we can do is, we can make this bolt bigger, and we can only make it in make it with 4 bolts. Also, if we are using this 8 bolts, then this won't be a through hole, so there will be 8 different holes. There we need 8 different holes, but here we need only 4 holes, because those will be through holes. So these are example of this eliminating of secondary operations and reducing the number of parts. Now another principle is don't assemble in confined space. We want to design in such a way that we have an open space. Here is an example when we have to do assembly in confined space because there is a wall here. So what we can do is that we will provide a wall on top of the component, and on the base there will be only a flat surface on which we can do assembly very easily. So we can redesign the part in a way that the assembly becomes easy. Also, tangling and nesting of parts while manufacturing or while assembly is a big issue. We many times see that the spring we are picking up are tangled with each other. Sometimes some parts we are picking come put some other parts with it. So how to avoid those kind of issues? For that, we can, the first is close up springs to avoid tangling. So if the spring end is open, there are chances that other spring will tangle in this area. If we close this end, then tangling chances will be reduced. Then these are some examples of how to avoid the tangling and nesting. If it will be a straight cut, then chances that there will be tangling. But if provide this kind of shape, if we provide this kind of shape, then there will not be any tangling. If there is an open end, then there are chances of tangling. If we close that end, then tangling is not possible. Again, if there is open end, then tangling is possible. Close that end and tangling will not be there. Then if there is some locking angle, then by increasing that angle, we will be easily remove the part, and we can change the angle. We can change the shape also to easily remove the part. And if we are using this type of parts, U-shaped parts, then they can easily be tangled. So to make sure that they do not tangle or they do not nest, we give some bands in outward curvature, so it will no longer tangle. And here are again some examples to how to eliminate tangling of parts. If you are using multiple wires, make sure that all the wires will go in a single larger wire, and the component at the end will have different shortcut or ports. So instead of three wires, now we have one wire only, and those three wires tend to tangle more, but the single wire will not tangle at all. Another things to be considered while assembly is to provide alignment feature. We see that while bolting or while doing fastening. Now if you are wondering why there are so much example with fasteners, because in assembly most of the time we are working with fasteners. So while designing for assembly, most of the time we are thinking about how to fasten parts and make it a assembly, and that's why we are mostly concerned about these fasteners. Okay, so provide alignment features. What do you mean by that? We mean that our part or design should have some features that will make sure that we do not need to align all the parts or all the holes. Consider this design. For this design, we need to align these two holes. Once those two holes are aligned, we need to align another two holes, and same way. But if we provide fastening screw here only, then we need not worry about alignment, because it will self align the entire wheel, and all we have to do is only fasten the bolts, only fasten the nut from the top. Similarly, here is another example. if we have this kind of design, then we need to worry about alignment of these both the feature. But if we have this kind of design, it will self align and we need not worry about alignment. So this is it for design for assembly. While designing for assembly, the most important aspects are reduce number of parts so that your assembly time will reduce automatically. If possible, try to avoid secondary operations and provide alignment feature. Provide features that will help reducing nesting of parts or eliminate nesting of parts or tangling of parts. Okay. I hope this session was informative because this is very important while we are considering design of assembly, and while doing any design this will be a very important aspect.